to the talk from Jonas Nick about privacy in Bitcoin or in blockchain, which is kind of the same, actually. So thanks a lot to LIIP AG for hosting us here. And yeah, let's start.
Yeah, thanks for the introduction. Yesterday I met a few old fellow students at dinner, and they asked me, how is Bitcoin doing? Are there actually more users this year than last year? And it was really hard to answer that, because you can look at the number of transactions, but what does it actually mean? So my answer was, well, 3 years ago I was at the Bitcoin meetup and we were like 6 people, and now we're like 30, so it's very cool that this community grew, and I would like to thank Lucas and the others again for really making this community grow. Okay, so this is going to be a technical talk. It's about a technical research topic, and we somehow forgot to mention this on the meetup page, so I would like to take a quick survey first. So, who would be able to explain the meaning of UTXOs in Bitcoin to me? Please raise your hand. Okay, for the recording, these are like 6 people. And who would immediately leave the room if I say this knowledge is completely necessary to understand this talk? Okay, 1 person. Okay, good. So everybody wants to listen, I see. Good that I explained it during the presentation, by the way. Okay, so this is about privacy in Bitcoin. And historically, there have been a lot of misconceptions and strong statements about privacy in Bitcoin. For example, kind of the first killer application in Bitcoin was the Silk Road, and they claimed to be an anonymous market. New York's Department of Financial Services, in an interview they said the major advantage they are providing is anonymity. And if you go to the Bitcoin wiki, what it says actually, Bitcoin is usually not very anonymous. Okay, so why do we want anonymity? Well, it's very important for a currency and to be private and also fungible, because who really wants everybody to know their payments to the doctor or to the bank or anything? A money which is not private, that cannot really work. So what do we want? I think we want anonymity per default, and also we want to allow for what could be called often selective transparency, which means that if I want to reveal to an auditor, to the law enforcement, my transactions, then I can do that. But I am in charge, and I can decide that. So the good news is that this is possible. We can get there. We kind of know how to go there. There are some trade-offs with scalability, but it's probably possible. But this talk is more about the other side, so there's a long road ahead. Okay, so what is Bitcoin? Bitcoin is pseudonymous, it's often said. And this means that entities, so persons or companies, they are represented by public keys, which I'm going to use interchangeably with addresses. So for the purpose of this talk, addresses and public keys are the same. And users, they can create as many public keys as they want. It's an unbounded number, actually. In Bitcoin, everything is known. It is known, the sender public keys is known, the recipient public keys, and the values of the transaction. So, the only thing that is unknown is the link to the entity. So, who actually owns that public key, we don't know. And this is very similar to a chat room, for example. I can give myself many names and chat in a chat room, and nobody would know who I actually am. And this kind of property, the pseudonymity, has initiated a research field called clustering, which is the problem that given a public key, find public keys which are owned by the same entity. and you're only allowed to use the blockchain, so you look at the transactions. So, for example, let's say there's someone in a chat room and he reveals his address or public key. And okay, so you know that public key belongs to that username, and then in the blockchain you see, for example, a transaction going from another address to some dating service. So now, using clustering, you could find out that those actually belong to the same person. And then you can conclude that Friedrich Nietzsche is actually a dog, for example. Okay, so now, to understand how clustering works, we first have to go a little bit into the details of how transactions work in Bitcoin. But the model that is used is kind of unintuitive, so I go with the intuitive model first, but afterwards you can forget it because it's only used in Ethereum. So now the balance-based model. So in this model, actually, the balances are represented in a global database. So you would see that Alice has 2 coins, Bob has 0 coins. And then when a transaction occurs, this global balance is updated. So then Alice has 1 and Bob has 1 coin. This is the balance-based model. And now the UTXO-based model, the one that Bitcoin uses. And UTXO means unspent transaction outputs. So in Bitcoin, you would basically say, what does it mean for a user to have 2 coins? That means that there are 2 transactions, or there are transactions with a value of 2 coins that can be spent by the user. So in this model, the balance is implicit, because the balance is exactly the sum of the values in the transaction that a user can spend. So now, if the user wants to send coins to Bob, she basically creates a transaction that spends that output, and now that output is not unspent anymore, it's spent. So now the balance is of Alice is just 1, and the balance of Bob is also 1. And this is similar to cash. When you, for example, if you get a $5 bill and a $10 bill, then your balance is the sum of it. And you can give somebody else this bill. Okay, so... And actually these kind of models, these are currently being discussed, which one is better, because people want to standardize on a model now. So maybe this is kind of interesting. I don't want to go into the advantages of both models, but for now we're just looking at the UTXO model. So let's look at a more complex example. So let's say there's a user U1 represented with a which is represented by a pub key U1, which has 1 Bitcoin. And again, in Bitcoin, that means that there's a transaction that can be spent by that user. And this is an output, because an output is just a value and a recipient of the coins, or the person that can spend those coins. So now, let's say the user wants to pay a merchant. So the merchant has an address M1, and the user wants to pay half a Bitcoin to that merchant. So what the user does, creates a transaction. So transaction here are always represented by boxes, and spends that previous output. And that output is now an input to that transaction. Okay, and very similar to cash, now we need to send the change back to the user. So the user generates a new address and sends the rest of the coins back to herself. Okay, so now the user wants to send 0.6 Bitcoin to the merchant. But this is in this output there's only 0.5 Bitcoin available. So, luckily, there's another output of the user in another transaction with 0.5 Bitcoin. And now what the user can do, she can spend both of them at once in a so-called multi-input transaction. So this now is a multi-input transaction. And now one technicality is that so in Bitcoin you don't directly send to pub keys, but rather you send to hashes of pub keys. And this becomes important later, but for now just keep that in mind for various reasons. Okay, so this was kind of important. It was very fast, so if you have any questions about that thing, how it all works, then please ask now, because the rest of the talk kind of depends on how this works. Yes?
U1, 2, 3 is the same user?
Yes. These are just different pub keys for the same user. Yes. Okay. So now let's look at clustering. Again, in clustering the problem is, given a pub key, find pub keys of the same wallet or the same user, and you use the blockchain to do that. And you can do that by using assumptions about the wallet behavior. This is why this is called heuristic. It's not, we can't be entirely sure that this works, but in practice it works. So, the first heuristic, it's called the multi-input heuristic. This was basically already mentioned by Satoshi in his original paper. And this simply says that all inputs of a transaction belong to the same wallet. So, for example, here if you have again a multi-input transaction and you know that your user has this pub key, then you would say, okay, this pub key also belongs to the user. Why? Well, it is just how wallets create their transactions, because usually wallets are alone responsible for creating transactions. So it's very unlikely that two persons coordinated and created a transaction together and then they spent their outputs. It's entirely possible, and we're going to cover that later. But usually people don't do that. So, next heuristic. That is called the shadow change heuristic, and this was introduced by a group at ETH. And this exploits the fact that basically the change is always a completely new pub key. At least in modern wallets, they create an entirely new pub key for the change. So it has never been seen before in the blockchain. And you can use that knowledge. Because let's say there's a merchant who has a static address, never changed this address, and then you see in the blockchain you see many transactions to that address. So now if you look again at the user, and now you have to distinguish which one is the change. Well, it cannot be this one because it cannot be M1 because it has been used before or seen before in the blockchain. So U2 must be the change address of this transaction. Okay, the next heuristic we call the consumer change heuristic, and the only reason why we can use it is because we are only concerned about wallets from consumers. We are not concerned, in this research project at least, we're not concerned about exchanges or merchant or some other companies which use kind of specialized wallets. So basically what we say is that transactions from consumer wallets have two or less outputs, because you just send to one address and then there's a change address, and that's it. You don't send to two addresses at once. So in this example we are paying to an exchange, and exchanges usually they make very big transactions because they want to save fees. And you see, okay, this address is used in a transaction that sends to many addresses. So when we know, okay, this is an address of the user, and now we have to distinguish which one belongs to the user. Well, this one, the exchange address, is not a consumer address because it is spent in a transaction sending to more than one address, so U2 must be the change address. Okay, next one is the optimal change heuristic. And This one was actually introduced by Christian Decker. He came up with this, and what you basically use the assumption that wallets do not spend unnecessary outputs. So, for example, let's say here in this transaction graph, now you want to distinguish which one is the change. Or let's see it the other way around. Which one is not the change? Which one is the intended recipient? If U4 was the intended recipient, then we would not have, we would not need, or it would not be necessary to spend that transaction. We could just have used this amount and sent 0.4 to our recipient. So this cannot be the recipient. This must be the intended destination. So now we know that this must be the change. In other words, if there is a unique output with a value smaller than any of the inputs, then this is the change. Okay, so the research question was actually how, so we know all this clustering, and some of this is in the academic literature. Some people try to do simulations, so they simulated some economy on the blockchain and then they try to evaluate how good is the privacy there. Our research question was how actually can we quantify privacy in light of these clustering heuristics, and this requires data. So you could go to every Bitcoin user and ask them, please give me your whole wallet so I can do a cool research project, and but users usually don't do that. So fortunately for us, we discovered kind of a vulnerability in wallet software, and I'm going to talk about next. So this is kind of a detour into that vulnerability that we used to collect data. So there are wallets which are called SPV wallets. Their defining property is maybe that they don't validate the whole blockchain, and they are therefore also called light wallets. And there's a special type of SPV wallets, namely they implement Bitcoin Improvement Protocol Proposal 37, connection bloom filtering. And so if you have this kind of wallet, it doesn't process the whole blockchain, but still somehow you need to know about transactions that affect your balance or that concern you somehow. And you use bloom filtering to do that. For example, wallets that use this is, for example, the Android Bitcoin wallet, Multibit and Bread wallet, and others which are not so frequently used. Okay, so now what is a bloom filter? It's basically a data structure which is used to efficiently test if an element is contained in a set. So it has two operations: insert, which inserts an element into the bloom filter, and query, which returns a boolean. So for either it is contained in the set or it isn't. And basically a bloom filter is characterized by a false positive rate. This means that this is basically the probability that the query returns true even though I have not inserted that element. So a bloom filter is a probabilistic data structure, and you can use it for efficiently testing, but then you have to, there's a trade-off with the amount of errors that you get, and this is called the false positive rate. And there are no false negatives. So, yeah, if you insert something to the bloom filter, then the query will always return true. If you have not inserted that element, it could be with some probability that the query returns true. So how is that used in Bitcoin? So we have a light SPV node which implements connection bloom filtering. When it connects to a new node, it creates a new Bloom filter and it inserts all pub keys and hashes of pub keys into that Bloom filter. Why both? Well, it inserts hashes because, as we said, transactions usually go to hashes of pub keys, and this is why the node is interested in these transactions. So when the filter is created, it sends to the full node. Now, whenever a transaction is received by the full node queries the data inside the transaction against the Bloom filter. And if the Bloom filter says, yes, this is contained in the set, then the node relays that transaction to the node. The node can then decide, okay, is it really interesting? Is it a false positive or not? So if it's a false positive, it can just drop that transaction. If not, well, then this is a transaction that the node is interested in. Okay, so why are Bloom filters used? Let's say, how can we, what would be another way to do this? So the node could just send all addresses to the full node. The SPV node can send all addresses. Hey, full node, I'm interested in these addresses. But yeah, for one, this Bloom filter has actually, it's more efficient for the full node, and we don't want to have a very heavy load on full nodes, obviously. And also, it allows us to get some privacy with Bloom filters. Why? Because due to the false positive rate, if a data element in the transaction matches, the full node cannot be 100% sure that it really belongs to the SPV node. So there's always some kind of uncertainty. You can reduce the false positive rate to 0. You would get a big filter, and then there would be no privacy for the SPV node. The other way would be to increase the false positive rate, then you had maximum privacy, but you would also relay every transaction. So that's very bad for mobile wallets, for example. So now, if you capture a Bloom filter from the live peer-to-peer network, and you query all addresses in the blockchain against it, you will get, or last year, the beginning of last year, you got 8,000 false positives. That means that you don't really, or there's a very small, or at least there's a small chance that the positives that you get are actually from that wallet, because usually wallets have only a few addresses, and the rest is just wrong. So you cannot really conclude a lot from this data. Okay, now the vulnerability. We know that the SPV node inserts both the public key and also the hash of the public key. That means that we can query both, basically, and only mark them as belonging to the wallet if both queries return true. And then, basically, the probability that this is a false positive, this is then the squared false positive rate of the Bloom filter. So it's going to be much, much smaller. In other words, now if you query the whole blockchain against that filter, you will only get one false positive, and all the rest are true positives that really belong to the wallet. So you can really, just by capturing Bloom filters, you can say a lot about the wallet. Namely, all addresses that are owned by this user of the wallet. Okay, so for 2 months we collected 37,000 filters from the Bitcoin peer-to-peer network. This was between December and February last year. And the way this works, you just connect to the Bitcoin peer-to-peer network, and then you need to be, basically, you need to fool everyone and say, okay, I have a lot of blocks, please connect to me. And then you will be picked up by so-called seed nodes, and these seed nodes will propagate your address to these SPV nodes. And then SPV nodes connect to your crawler, and will send their Bloom filter to the crawler. Okay, so this was only the way how to get data. And we were very lucky to find this. Sorry. Okay. So, what can you do with that data? You can do stuff that is usually very hard to do in analytics of the blockchain, because now you can, for example, plot the distribution of the size of wallets. So, for example, here the data we collected, we know that more than 50% of the wallets just had one pub key. And around 20% of the wallet had maybe 2 addresses. So it kind of follows a power law. I guess that is also what you would expect. And you can, for example, also compute the total received bitcoins for that wallet. So you see that more than 50% received between 0 and 1 bitcoin, and around maybe, let's say 12% or something received between 1 and 2 bitcoin. But we also had a wallet in there which received more than 60,000 bitcoin. Okay, so what can you do about this? This issue has not been fixed yet, so you could do the same right now. And why? Because to really fix it, you would require a modification of the protocol. And this has been, or there are some suggestions of how to do that, but to my knowledge, nobody is currently actively working on a fix. So, alternatives are, if you are a privacy-conscious user, and you should be, you can use the other type of SPV wallets that don't use Bloom filters. They need to connect to a central server to basically learn about the addresses they are concerned about. So, yeah, you could use a central server. That's probably also not ideal. At least not if you don't trust the central server, or you need to use a full node instead of an SPV node. Okay, so our goal was to evaluate clustering. So now we have collected the filters and we reconstructed all pub keys of each individual wallet. So now we can apply clustering and then see how well does clustering actually work, because now we have kind of the ground truth. And as performance metrics we use precision and recall. The precision is the probability that a pub key is really in the wallet given that it was found by the clustering heuristic. The recall is the probability that it is found by the heuristic given that it is in the wallet. So, for example, in this transaction graph, and basically we apply the multi-input heuristic, let's say, to U2. Then we find U3. So we have a precision of 1, because the pub key that was found really belongs to the same wallet. And a recall of 2/4, because we only find 2 pub keys of the whole wallet, which has 4 pub keys. In general, we are more interested in the recall because we assume that the precision is very high, because the heuristics exploit wallet behavior, and we kind of know how wallets behave. We can read their source code and observe them. But it's really interesting what the recall is, because this essentially means if you give me 1 public key, how many public keys of your wallet can I discover? So, these are the results. For the recall, I'm only showing the recall because the precision is more complicated. This is kind of the baseline and simply says, I'm not applying any heuristic. You give me a pub key and I have this, I just don't apply any heuristic to that pub key. And because there are many wallets which only have one pub key in them, this mean recall is already pretty high, because for wallets which only have one pub key, the recall then is 1, if you don't apply any heuristic to it. On the other hand, we have the best possible value. This is basically if the clustering heuristic was perfect and would always discover pub keys which are used in the same transaction and belong to the same user. And in between, you have the clustering heuristics that we described before. And for one, you see that all of them are closer to the best possible heuristic than to the baseline. And you see there's, I mean, here, I'm going to show graphs in a minute, but it seems to be small, but it's actually quite a jump. And what we do is we combine those heuristics together. So if you see multi-input here, this means multi-input heuristic alone. Shadow means multi-input plus shadow. Consumer means multi-input plus shadow plus consumer. Yeah, and so on. Okay, if you look at a graph of, this is on the x-axis you see the size of the wallet, on the y-axis you see the recall. The gray line is again the baseline. This is just 1 divided by the wallet size. This represents if I don't apply any clustering heuristic. And the blue line shows the multi-input heuristic. And what you see, for example, if there is a wallet of size 5, you will find, given one pub key, you will find 40% of the pub keys contained. And this is 20% more than what you would find, or what the baseline is, not applying any pub key heuristic. Okay, and here you see basically all of the heuristics. The violet one is best heuristic, and you see green is the shadow heuristic, so this helps quite a bit. And the other two, consumer and optimal, they don't have so much, but at least it looks like that in the graph. But if you look into the data, they both helped at least in 1,000 wallets. So they improved the result in 1,000 wallets each. Okay, in conclusion, we captured the public keys of 37,000 wallets from the Bitcoin network. We introduced two new clustering strategies. We evaluate the performance using the ground truth, and on modern wallets you will have a 70% recall. This means that if you give me one pub key, then I will find 70% of your wallet on average. So now, few of the countermeasures. So one is keep your wallet up to date. Yes? Just one.
So your data is based on you only have the LIIP nodes.
Yes, yes,
so
yes.
Do you know the distribution? How many wallets are based on LIIP nodes and how many run full nodes?
That's a good question. I know how...
So you only have these 37k wallets and you don't know how many wallets there are?
Yes, that's true.
Okay.
Okay. So during our experiments, I mean, you can run a crawler in the network, and then you see basically so clients send you their version message, and then you see, okay, many of the wallets are out of or are really, really old, and they have worse privacy properties. For example, they have a false positive rate of basically 0, so you don't need even to exploit anything, because you can just see the addresses that are contained in that wallet. So you need to keep your wallet up to date. If you're privacy conscious, unfortunately you should not use wallets with Bloom filtering. Do not reuse addresses. This is kind of the standard recommendation. So you should always create a new address when you give out an address. So when somebody intends to send you some bitcoins, create a new address. What is also important is that the party you're transacting with also plays a role in keeping you private, because if the other party reuses addresses, then it is easily distinguished with a shadow heuristic which one is actually the or it's easily distinguished which one is change and which one is the destination. So you need to keep that in mind. A general recommendation from operational security is to separate. So maybe it might make sense, some wallets they have an accounts feature, so you can have multiple accounts. Maybe it makes sense, for example, to pay paying your doctor's bills to create a new account. A web page or kind of a project which is dedicated to user privacy in Bitcoin is openbitcoinprivacyproject.org. They evaluate wallet software. I don't agree mostly with their conclusions, but still they list a lot of criteria how to evaluate wallets, so I still think that is valuable. And there are interesting altcoins that are more or less mature, and some of them implement very nice privacy features. So what some users actually do, they exchange their bitcoins for an altcoin, let's say Monero, and then they transact a little bit and then they send it back to Bitcoin. But this is actually not that good. It's because you can easily see on the blockchain, using just the values, okay, there was some outflow of Bitcoin, and then you see the same inflow again with a similar value. So that is you can see that in the blockchain. So yeah, I don't think that this strategy really helps. As long as there's no economy in altcoins. If there are exchanges in Monero or Zcash, then the situation changes completely. Okay, so very short, for developers, what can you do if you are a developer and now you want to improve privacy in Bitcoin? There are a lot of suggestions what you could do, so I'm only going to focus on the most practical ones, I think. One is coin selection, and coin selection is the way by which wallets decide which unspent transaction outputs they are going to spend. So, for example, you could say, please, wallet, always spend all the transactions going to the same address. So then the reusing addresses wouldn't become such a problem. So basically, you would, for example, in Bitcoin Core, you would introduce a flag or something where you would say, okay, please, privacy-aware coin selection. Another interesting thing is CoinJoin. And CoinJoin works by merging transactions of multiple users into one big transaction. So let's say you have two transactions and you can communicate. So Alice transaction, Bob's transaction, Alice and Bob communicate, so they can create one big transaction which does exactly the same, but now it is impossible to tell which input belongs to which output. And this increases your anonymity set, because yeah, you cannot see anymore who actually is the sender of this output. Okay, and there exists a trustless, or it's basically that's the standard way how it's described as a trustless way. So nobody, you don't need, if you are Alice, you don't need to trust Bob or something. There's no way that Bob can steal your coins. But in practice it turns out that the user interface and the exact protocol is very challenging, because if Bob misbehaves, he could try to start a denial of service attack and so on. So this is quite challenging. One the issue with the user experience is that, of course, if you want to merge transactions, these transactions need or these outputs need to have the same values. Because otherwise, if it was one Bitcoin here and one Bitcoin here, you would easily see which output belongs to which input. And so, in other words, you always need to find someone who wants to exactly use the same amount. And there is some cryptographic innovation called confidential transactions, which means that you encrypt transaction values. And when you encrypt transaction values, this helps in the finding a partner for your CoinJoin, because now it's basically irrelevant what the values in the transaction are. But yeah, this doesn't exist in Bitcoin yet, and it will probably take a while, or maybe never even get into Bitcoin. Not very confident about that. Okay, and so CoinJoin is a really cool protocol. It's not that difficult, but unfortunately it has not yet gained a lot of adoption. The only application that implements CoinJoin is called Join Market. And this is very, very cumbersome to use, because you have to use Bitcoin Core and some Python application. No regular user can use that. But it's kind of a neat proof of concept, because in Join Market, users basically, they sell CoinJoins. So they say, okay, I sell a CoinJoin for 1 Bitcoin maximum, and I take a fee of 3 Satoshis, say. Yeah, and this is actually used by people, even though it's just a proof of concept. So, my recommendation for developers: choose a wallet which is popular, implement a plugin that connects to Join Market and does the CoinJoin and implements the Join Market protocol. I think that's the most practical way how to go forward. Okay, thank you. This was the research project. Do you have any questions at this point? Also going to be staying for the restaurant visit, so yeah. No questions? Peter?
In the case of Join Markets, is there no central server that learns about the transactions that get linked together? Or how do the participants find each other?
Okay, right now it's basically it's an IRC server, but the participants, they basically use encrypted communication, so the IRC server doesn't learn anything. And I should probably add that this has not yet been reviewed by academics. There are a few papers about this. I'm not 100% sure that you can, or that is actually 100% secure, so there. Yeah, how do I explain? It doesn't really matter, but I think it's much better than the current situation. That's for sure. Yeah.
The chart is
the chart you showed about the number of nodes and then how the percentage develops over number of nodes. It's intuitively clear that more addresses actually have in your wallet, the safer you are. But I was astonished to see the best. It's actually going up with the number, with the size of the wallet. Yeah. Is there an easy explanation to make that possible?
Yes. The easy explanation that this is kind of an artifact of the evaluation method. Because, as I told you, even if you use the vulnerability in Bloom filters, there's still one false positive. And this one false positive can completely destroy your analysis. So this is why we use some statistical methods to try to get rid of this thing. And yeah, basically, everything is described in my thesis, but this is just an artifact. So this is an artifact of there's not enough data of wallets with 30 pub keys. Okay, no questions?
actually have another one.
Yeah, okay.
if you know these heuristics as a user, one thing that came to my mind is that I tried to beat them by, if I generate a transaction, I try to generate parts of the change myself by actively having more outputs then, and could I not increase privacy that way?
Yeah, that has been proposed. I don't know, I think it really depends on how you do it. I think it's a good idea, but on the other hand, so usually you have two outputs in a transaction. So the probability of guessing the correct one is 50%. If you have three outputs in a transaction and two of them are yours, then the probability of guessing the correct one is more than 60%. So if you look at it that way, I think that it could even be worse if you add multiple change addresses.
But I may not know that there's two.
Well, if I see, but you cannot really assume that your attacker doesn't know which wallet you use, because your wallet basically leaves a footprint on the blockchain. So I could try to distinguish different wallets.
So, does this actually work, this microphone? Yes. Oh, I see. I see. So, one strategy that has been proposed years ago is whenever you create change, you create two change outputs, one with the same amount as the amount you're actually sending, and one with some remainder, and try to sometimes make that larger and sometimes make that smaller than the amount being sent. What do you think about that strategy?
Yes, I mean, one issue then is, of course, maybe you want all transactions of the blockchain to be as uniform as possible. Because I could maybe distinguish you because I just see, okay, you use 3 outputs, regular users use 2, so I can see what your changes.
And I'm the only user in the world of Awesome Wallet which uses this, so you
Bitcoin Core.
Sure. Anyway, fine.
Yeah. Okay.
And that implies that you're rich. When the change.
What's the wallet you would recommend regarding this privacy?
I would recommend Bitcoin Core with using Tor, maybe.
Okay.
But you still, you have to generate a new address, right, every time you use it. Probably what I would use.
Any light wallets?
You can use Electrum, for example, and you can use your own Electrum server.
Which means you're still running a full node.
Yes, you're running a full node, but you can still use it on your phone. And I've never tried this, but people do this, I think.
What's your opinion of dark wallet in this regard?
I don't know. I haven't been able to use it because it's kind of in a beta or alpha stage, and my Chrome always crashes when I try to use it. So, I don't know.
It's perfectly secure because you cannot create any transactions.
True.